Alright, let's answer question 14 and 15 together, since they are about the same topic, coupling maps. So, what is a coupling map? I was really confused when I first looked up this question. But eventually I learned out what it was, so I'll tell it to you quick. It's a directed graph that represents the physical coupling of a system. And the nodes are labeled by integers, and they represent the physical qubits. So 0 represents Q0, and 1 represents Q1, and so forth. And a directed edge between two qubits means that a CNOT is permitted between the two. So let's look at that example. Let's build some intuition behind this. So let's say we had a physical system where the qubits were in some sort of lattice, like this. I guess I forgot Q0. It's okay. So this might very well be what the quantum system is using, a lattice of 6 qubits. And so if we think about it intuitively, a CNOT, we can't always do a 2-qubit operation on any qubit that we want. Right? If we wanted to do a CNOT between two qubits that were separated across the room from each other, I don't think that's possible physically, because like the CNOT is used in quantum entanglement, we can't entangle two quantum bits that are separated across space. They can be still entangled across space, but to make them entangled, I don't know if it's that even possible. No one else has told me it is. And so that makes intuitive sense in this format, where we're restricted to what coupling we could do. Because these qubits are too far away, we can't do a CNOT between them. And also, if we were to try to do that, we might affect Q2 and Q6, since Q2 and Q6 are closer to Q3. So each physical system is limited in which way it can do CNOTs by actual physical space. So if I did an arrow from Q3 to Q6, that means I could do a CNOT from Q3 to Q6. So I did a graph up here. This means I can do a CX from 0 to 3, or from 0 to 1, or from 4 to 1, I'm just choosing some, so forth. So the control is the source, and the target is the destination. That's how it goes. It's a directed graph, where the edge and the direction matters. So that means I shouldn't be able to do this, because those qubits are not coupled together. They're not close enough together. I shouldn't also be able to do this. But as you've tried in IBM Quantum, you can. And if you create whatever circuit and see the results, and you do it on math, you do the math by hand and figure out what the results should be about, and then you get the right probabilities in your sample, then you know that you can run any quantum program. I've never seen an error when I'm running quantum programs that says I created a quantum circuit that was impossible to be implemented on actual quantum hardware. And that's because it does in the transpilation mode, which I'll write that down here. In the transpilation mode, so transpilation, which is a combination word, fancy word to say transformation plus compilation. So it transforms the quantum state into a new quantum state, or it transforms all the gates into gates that actually can be run on the quantum hardware. Right? The physical gate that represents the Hadamard is actually three gates, a series of an R rotation Z, and then a square root of X, and then a rotation Z. And so to do that transformation, to create it into the actual basis gates, we call it the transformation process. And during that transformation process, it does an NP-complete algorithm to map the CNOTs to actual CNOTs that can be used. Because we can't do a CNOT from Q0 to Q4. But it will figure out a way to do that through swaps. And that way we can reuse these qubits. And then it will compile the quantum code. It'll compile the Python that you created for this into actual quantum instructions that the quantum computer can run. So question 14, now get into the questions. Which code snippet would execute a circuit given these parameters? So we want to measure 1024 times, so that's looking like the shots we want. And we want to use the chasm simulator, that's how we get the chasm simulator. And we want to use a custom coupling where the 3 qubits are connected linearly. So that would look something like this, where Q0 connects to Q1, which connects to Q2, because that's a line. And that looks like it's this. Looks like this one is it. This is an adjacency list. So the first 0 means 0 connects to 1. So this is the control and this is the target. And these adjacency lists specify which way the edge is going to be. And it's a list of lists. So this is looking to be the right answer, because we have our back end here, which is the correct way to give it. And coupling map is a keyword that we can use. So answer A is the right answer, but what about B, C, or D? So we have a syntax error there. Should be get underscore backend. So B's wrong. C, we have repeat instead of shots. So that's a wrong keyword. And D, I have shot instead of shots. So should be able to answer that using the documentation. And then for 15, which of these would execute a circuit on a set of qubits which are coupled in a custom way? So now we want a custom coupling instead of a linear coupling. Well, we can use any coupling we want, but we know that this is a keyword. So that's the right answer already. But what about this one? That's not a keyword either. And device, we give that with backend, so I should be coloring this red. Anyways. And D, so all these are the wrong answers since they use the wrong keywords. And there you go.